Let's look at the acid dissociation reaction for a generic acid, HA. So we have HA reacts to give us H plus proton and the conjugate base, A minus. We can then write the acid dissociation constant, the equilibrium constant expression for this reaction. So we have Ka is equal to the hydrogen ion concentration times the A minus concentration, the conjugate base concentration, divided by the concentration of HA, our generic acid. Let's then take the logarithm of both sides. So we have log of Ka on the left, and we have log of this whole equation, this whole expression, on the right. And so over here we have this term, log of Ka. This is similar to the pKa, where the pKa is equal to minus log of the Ka. So this term is the negative pKa. And over here we have this log term with a lot of stuff in it, but let's break these out. Because one of the properties of logarithms is that if we have log of x times y, we can separate those into log of x plus log of y. And so let's separate out this hydrogen ion concentration into its own log term. And we'll leave these two together in one log term. And now we have here log of the hydrogen ion concentration. And again, just like we had for the pKa, this is minus pH. So we have minus pKa equals minus pH plus this log term. And now let's swap the sides of these two. So let's add pH and add pKa to both sides. So we have pH equals pKa plus that log term. And this then is the Henderson-Hasselbalch equation. And so this then relates the pH of a buffer to the pKa of the acid and the log of the ratio between the concentration of the acid to its conjugate base, or rather the concentration of the base to its acid. So suppose that we have equal quantities of the acid and the base. That means that the ratio of this fraction is 1. The logarithm of 1 is 0, which means this term is 0. And that means that the pH is equal to the pKa. So if we add equal quantities of an acid and its conjugate base, that means that we will have a pH equal to the pKa of that acid. But in addition, if we add a small amount of acid or base, we'll convert some of the base into the acid or the acid into the base. But we won't be changing this fraction by very much. In fact, in order to change this log term by a value of 1.0, we need to change this ratio by a factor of 10. We need to have 10 times as much of the base as we had of acid, or vice versa, which means we need to react away most of the acid or the base. And this means that as long as we have a roughly equal quantity of acid and base, we have a pretty good way of resisting the pH changes by adding or removing acid or base. And this is then what we call a buffer. We have buffered the pH where the pH won't really change very much until we add a huge quantity of acid or base to dwarf these concentrations. So let's talk about safety. The hydrochloric acid, sodium hydroxide, and acetic acid that you'll use in this lab are all corrosive to human tissue. Clean up any spills immediately, and if any touches your skin, wash the affected area immediately.